didn't get your exam, I'll pass those back to you after class if you want. Okay, so I had a couple questions about your homework problem, and I was planning on going over it anyway today. We've done problems with electricity where we had charges in a particular arrangement and talked about the forces exerted on this charge due to this charge, all that stuff. This is somewhat similar, but with magnetic forces, which immediately make it more complicated because the geometry is somewhat obnoxious. So this is a problem similar to your homework problem. We're going to go through some of the geometry. I also have a video on my YouTube playlist that deals with this specifically. I would encourage you to watch it. I will also tell you that your lab quiz tomorrow will be something similar to this. At least you're not going to have to work through the whole problem because it takes quite a long time. But I just want to make sure you understand the geometry of what's happening. So this is very similar to the one on your homework. You have three long current carrying wires. They labeled them I1, I2, and I3. Your homework gives you some values. That's not super important to me right now. But they form the corners of an equilateral triangle of some distance d. So they're all the same distance from each other, basically. And you're asked to determine the force on each of the wires. And that's, well, actually it says you're asked to determine the force per unit length on each of the wires. So let's first deal with that. What does that mean, force per unit length? This is a trick we sometimes use to make things simpler for us. We have this expression: the force on a wire that's carrying a current I in a magnetic field is given by this, where I is the current. L is a vector that goes along the length of the wire, right? There's no guarantee that it's straight, but we're going to consider it to be straight. But L is a vector that goes along the wire. The vector would be straight. There's no guarantee the wire is straight, so you might have to integrate this in the general sense to go over a whole wire. The whole point is this is some sort of path that the wire takes. And then cross magnetic field, where I is the current being carried by this wire of length and dimension L. This is the magnetic field in which the wire is contained. Okay. We usually deal with in the really simple case, where we have a straight wire that's oriented perpendicularly to the magnetic field. If it's oriented perpendicularly and if the thing is straight, this just boils down to a really simple, if I take the magnitude, just I, L, B, right? This is a simple case. So you have where I is the current and L is now the length of the wire, right? The idea is if you sum up the contribution over the whole wire, then you get the length of the wire. In this case, they don't tell you what the length of the wires are, and you can't even see it because it's coming out of the board and going into the board. What they ask you for, though, is the force per unit length, right? So just divide out the length here. And then you get this expression for force per unit length is IP, right? That's all it is. It's a pretty normal thing for people to ask when they don't want to deal with the length of the wire. So this is what they're actually asking you for, just in case that was confusing. They want the force per unit length. It's just this expression with the length moved to the other side. All right. Now, with that in place, once I have that, let me move this over. So now let's ask ourselves the question. Let's pick out this one, which I've labeled I1. Right? So if I want the force per unit length on this wire, then this I is the current being carried by this wire. And the magnetic field B is the magnetic field in which that wire is encased. Right? So let's ask ourselves the question. Is there a magnetic field in which I1 finds itself? So you're shaking your head, yes.
Yes.
Where does that field come from?
The other two wires?
Yeah. So remember, just like every charge is the source of a every charge is the source of an electric field, every moving charge is the source of a magnetic field. Magnetic field have their sources in currents, moving charges. So there are two other currents on this board that are producing magnetic fields. I1 is going to find itself interacting with the magnetic fields of those two wires. So the first thing we got to do is figure out what those fields look like so that we know what to put in here for B, right? The geometry is going to get a little complex, so just stick with me. Ask questions if you have. Stop me and ask if you don't see what I'm doing. So the first thing I would say is let's just look at this current here and see if we can figure out what the magnetic field line due to this current looks like. I've got a long straight current, which means I need to use my right-hand rule for fields. Well, okay, I've got a long straight current, and I want to know the field. Right-hand rule for fields says your thumb goes in whatever's straight, and your fingers tell you whatever's curved. What is curved here? The current of the field. Sorry, what is straight here? The current of the field.
The current.
Current, so it's a long straight wire, right? So your thumb goes in the direction of the current. That's into the page. Your fingers then tell you what the field does. It wraps around. So if I were to draw the field line here, it would look like that. It goes around clockwise. And the same over here, right? This is also going into the page. Now, that's not the same thing as the field at a particular point. The field line is a representation of a bunch of vectors. Remember, vectors are always straight lines. Field lines can curve, but the vector field at any point is always straight. And in this simple geometry, it's always tangent to the field line, right? So if I were to ask you, what does the field look like right there, right? And I've picked out the point where this field line intersects this imaginary line connecting the two currents. It's going to be tangent to this field line, which looks like this. Right? So that's the field at that point. The field at any other point would be tangent as well. But look at the geometry here. Do you agree that because of the way this is oriented, this dashed line lies along the radius of this circle? Yeah. So just because it's going in a straight line basically from this current, it's going to lie along the radius of this circle that I've drawn as the field line. Well, tangent lines and radial lines, by definition, are perpendicular. So, there's my first geometric relationship. This imaginary line is perpendicular to the field line here. Everybody see that? All right. Now, expand your picture, right? I've drawn one particular field line here. But I could draw others, right? These field lines are going to form concentric circles moving out from that thing. So there's a circle here, and a circle here, and a circle here. I'm not going to draw those because it's going to get really convoluted, but you can kind of see it, right? There is a field line which passes through this point. It forms a big circle, looks like this, right? Okay. What does the field look like at this point due to this? It was just going to be a tangent line to that circle, right? Just like this is a tangent line to this circle. I'm drawing it down here so you can see it. But up here, it's going to look like that. Tangent to the circle. Draw the circle in if you want to. And what I've done now is I've determined the field B due to I2. We're calling this I2. That's the field due to I2 at the position of this wire, because this is what we want to know the force of that position, right? Okay. Now, here's the critical point. This is also perpendicular, right? This still forms a radius of that field line, which means the field at that point is going to be perpendicular. All right. Now, let's go through some of the geometry. What is the angle of the vertex of that triangle? Say it loud. Hasn't been that long since 10th grade geometry, right?
60.
Yeah, equilateral triangle, every vertex is 60 degrees. So, we've got 60 degrees here. Okay, now, what we're saying is from this dashed line to this vector is 90 degrees. It has to be perpendicular. I've covered 60 of it between the two dashed lines. What's left over? 30 degrees. 30 B due to I2. All right, fair enough. Let's continue on with some geometry. Probably, I'm going to need a horizontal line because I'm going to have to resolve some vectors, right? So there's that horizontal line. Now let's see what we can do here. But basically, this is going to serve as your x-axis, right? Okay. What is the angle between this dashed line and this side of the triangle? 60 degrees. How do you know? Can you see your way through the geometry?
5.
Yeah. Imagine this as, well, let me draw this. Not the only way you can get here, but this is one of the ways I think about it. If I just draw, so I have this triangle, and this triangle, right? I've made half of a hexagon, right? I know this covers 180 degrees. These are all equilateral triangles because the hexagons are made of equilateral triangles. That's 60 degrees. That's another 60. That's another 60. Put them together, you get 180, right? This is the angle I'm looking at right there. So this, from here to here, is 60 degrees. I've covered half of it here. What's left here? 30 degrees, right? Okay, why do I care? Well, what that means, if I take B, I2, I can now resolve that into x and y components. The angle this makes with the x-axis is 30 degrees. Therefore, BI2x is going to be BI2, whatever that is, cosine 30 degrees. And BI2y is going to be BI2 sine 30. Everybody okay with that? Okay. I'm going to erase some things to make this less convoluted. So do we all have the graphics here? Let me get rid of this and this. But we know that that's 30 degrees. Okay. I'm going to do the same thing with the magnetic field from this one. Right? If I were to draw it here, it would look like that. Translate that up. Draw bigger and bigger concentric circles. This is still a radius of those circles. At this point then, that will look like that, where this is the field from I3. Okay. This line and this dashed line, this vector, this dashed line, are perpendicular because same thing. This dashed line functions as a radius. This is tangent. They're perpendicular. So, okay, we'll see what we got here. All right, from this vector to this dashed line is 90 degrees. I've accounted for 30 of it here and 30 more of it here. What's this angle here? 30 degrees, right? If this is 60, that has to be 30. So here's another 30 degrees. That means that I could write also, this is BI3. BI3x is equal to whatever that is, BI3, cosine 30, and BI3y is equal to BI3 sine 30 degrees. We okay with this? I left one thing off. Look at my original BI2y. That's right here. Is the y component going to be positive or negative?
Negative.
The very least we can say is it's going to be opposite of whatever that one is, right? So let's go ahead and assign up as positive, which means that is negative. And we've basically taken care of the geometry. Questions about it? It's not trivial to find your way through that. Everybody see what's going on? Okay. Now, we haven't really answered the question yet. So let's continue on and try to do that. what I've done is I've determined the field components. But this B is the total field, right? Both of those sources are going to put some stuff together, and I'm going to have to add those up vectorially to find out what the total field is there. Right? So, how do I do that? Well, first of all, let's figure out what BI2 and BI3 are themselves, then we'll worry about the components. We have for that this, which comes out of the Savart law. The magnetic field due to a long straight wire is mu naught I over 2 pi, and your book gives you a capital R. What is the capital R? It's the distance between the source and the point you care about, what we've called D. Okay. And I is the source. This is just your general formula. But what this means is that BI3 is equal to mu naught I3 over 2 pi, and as long as we're talking about at that point, I can put a D here. It also means that BI2 mu naught I2 over 2 pi. Again, equilateral triangle, everything's the same distance, so I can also put a D here. That works because I'm looking at it at the same point. Okay? All right. So, let's go ahead and take care of some trig. Those of you that I just worked on with know I had trouble finding my way through this. So, if you haven't studied special triangles, that's okay, but they really help. Most of you took pre-cal. Anybody here take a dedicated college trigonometry course? Yeah. Good. Most of you took pre-cal, right? Nothing wrong with pre-cal. But you don't get as much as you want. Did you study special triangles in your trig course? Yes. What's the sign of 30? Putting you on the spot. Yeah, it's terrible. Special triangle, right? 30, 60, 90 triangle. Right? This is 1, 2, square root of 3. Always. So, what is the sine of 30 degrees? One half. What's the cosine of 30 degrees? Root 3 over 2. Yeah. I think they did this in Expert TA intentionally so that you could deal with it without having to deal with a bunch of decimal points, right? Just leave it like this, that'll be fine. Not all geometries are this pretty, but for equilateral triangles, it actually is. So, what that means is that I can now say this: whatever my resultant field is, right? And as I've drawn it, it looks like this one is bigger than this one, which means this current is stronger than that one. That's actually how it is in your Expert TA problem. There's no guarantee of that though, right? But wherever my resultant vector is, it's going to be somewhere. What color have I not used? I think I've used them all. I saw another one. Yeah, it's okay. I'll use green again. Whatever my resultant is, it's somewhere in between those two, right? That's what I need to find. So I find that with this Pythagorean theorem. Right? This means that B resultant is going to be the x components of these added together, squared, and added to the y components of these added together, squared, to take square whole thing. It's Pythagorean theorem, right? So what does this mean? Let's get the x component first of my B resultant. That's going to be x component of this, right? Which is going to be cosine. So I get mu naught I3 over 2 pi d times the cosine of 30 root 3 over 2 plus x component of this, mu naught I2 over 2 pi d root 3 over 2 cosine of 30. Right? That's the x component of my result. My y component, that's going to be I3, mu naught I3 over 2 pi d times the sine of 30, 1/2, minus, because that goes down, right? Mu naught I2 over 2 pi naught over, I'm just going to write it like this, over 2 pi d root 3 over 2 I3 plus I2. That's my x component of my result. And the y, I get mu naught, oh, yeah, that's right, over 2 pi d 1/2 I3 minus I2. You can do a little bit more algebra here if you want to, but I'm going to leave it like that. Because I think it's obvious here. This is the cosine, and this is the sine. You can put it together if you want. Okay? Any questions about this? Well, what do you do from here? Well, Pythagorean theorem. This is the x and y component. You square them. You add them together. You take the square root. It's not going to be pretty if in this form. Now, I will say, in Expert TA, for this problem, they give you something, well, I'll tell you what they give you. And you don't have to write this down now if you want to. But they give you that this is, what is it, 5 amps? I think they give you that this is 5 amps, and this is 10 amps, and this is 20 amps. Now, when I see that, I immediately go, you know what? That is I. This is 2i, and this is 4i. Because what happens when I do that? I get a number in these parentheses, and an I that comes up here, right? I might get I plus 2i, that just gives me 3i. It makes the algebra so much cleaner, right? That's what I would do immediately. But as you do, right? But the important thing to me is that you get something that looks like this. Then you can put that together to find your resultant. Okay? Does that make some sense? The geometry is tedious. These are not short problems, but they're doable if you can see it. Alright. I'll leave the rest to you to finish. But the last part of that question, Expert T asks you about the direction of the force. So you're going to go through here, you're going to determine a B, and then you're going to put it in here. Right? This is IB. So all you're doing right now is finding B, and then you put it in here, and you're going to find the force per unit length. But that doesn't give you the direction of the force, right? So what we're saying is whatever this guy is here, this is your resultant. Whatever he is, times this current gets you the force per unit length. But what direction? Well, you now have a right-hand rule for forces. We did the right-hand rule for fields, which is thumb goes in whatever is straight, fingers goes in whatever is curved. Right-hand rule for forces, though, says you put your fingers in the direction of the current, curl them towards the direction of the field. In this case, the current's coming out of the board. My fingers would go like this, curl them towards the field, which goes like this, and then stick up your thumb. And I'm going to get a force on this one that looks something like that. Quite a bit of geometry to get through to find that one too, but you can do it. Okay, questions about that? This is not a short problem. I don't think it's a hard problem physics-wise, but the bookkeeping is quite rigorous. You got to really keep track of everything. Questions? Like I said, there is a video on the geometry here that I have on my YouTube playlist. You should check it out. You go through it slowly if you need to. Because once you see it, so you get it, but it takes a while to see it. Any questions at all? All right. Then we're going to go a little bit into the last thing from chapter 12. I'm going to try to move on into chapter 13. Chapter 12 has been about the sources of the magnetic fields, right? We've talked about how to determine the direction with right-hand rules of fields and currents. Then we looked at the Biot-Savart law, which says magnetic field is equal to mu naught. I'm going to pull out the I, although it's not technically always out of the integral. And then we have d I believe it's L cross R hat over R cubed, no, R squared. In your book, I is inside the integral because IDL is the current, and there's no guarantee that I is not changing, so they leave it in the integrand. In this class, we're not going to deal with it when it's not changing, so I'll take it out. But this is about Savart law, right? And we figured out that it's not the easiest thing to evaluate. Cross product really kind of screws you up here, or at least it can. Now, the ones we've done and the ones I expect you to be able to do are not super complex, but they can get really, really complex. And so we saw kind of the same thing when we did Coulomb integration, finding the electric field by direct integration, right? If the geometry is simple, then it's no big deal, but if the geometry is wacky, then it's really obnoxious. So what came to our rescue? Gauss's law, right? We said, okay, if the geometry allows it, Gauss's law gives you a much simpler way to get to the electric field. Something similar is going to happen here. I will say there is a Gauss's law for magnetism, but we don't study it in this class. We're going to study this thing, which is called Ampere's law, which functions to Gauss's laws, functions to magnetism, kind of like the electrical Gauss's law functions. It gives you a way to get to the field easily if the geometry allows it. So let me just put down what this is, and we'll talk about it. We're not going to go super far into this. We're not going to be super rigorous with this, but we are going to talk about it. So Gauss's law says this. No, Ampere's law, not Gauss's law. And for some reason that I have not yet figured out, I like it. I really do. But every book has some quirks, right? This book just seems to have more quirks. I like your book mostly because it's free for you guys. But your book does not include the enclosed here. I don't really get that. It should be there, right? Right? If you have a physical textbook, write it in. If you don't, make a little note on your PDF or whatever. I enclosed. Well, what does that mean? Well, let me remind you what Gauss's law said. E dot dA is equal to Q enclosed over epsilon. This is Gauss's law. First thing, an integral symbol. This is a closed path integral. That's why the circle's here. That means whatever's in here, whatever your integration variable is, you get back to where you started. So in this case, it's a dA.